Sept, most of you know, it's the Information Sciences and Technology Center. We do a lot of activities both on campus and in the mountain states through RMAC, which is Rocky Mountain Advanced Computing Consortium. So some of the activities we do at CSU include this distinguished lecture series. Some of you were here in this room a few days ago when we had the Fort Collins Broadband Initiative debate. Like on Wednesday, we will have this workshop on Summit. If you are interested in using the Summit supercomputer, or if you are a user, you are welcome to attend that. The registration is open. And today here we are here for the second lecture, second distinguished lecture this semester. And it's my great pleasure to introduce Professor Mustafa Amma, whom I have known for about 3 decades now. So Mustafa Amma is a Regents Professor with the School of Computer Science at the Georgia Institute of Technology. He has been with Georgia Tech since 1985. He received the SP and SM degrees from MIT and PhD from the University of Waterloo, Ontario. His research interests are in network architectures, protocols, and services, and he has published extensively in these areas. Has graduated over 35 PhD students. Many have gone on to distinguished careers in academia and industry. He has served the networking research community in numerous ways, and most notably, he served as the editor-in-chief of the IEEE ACM Transactions on Networking from 1999 to 2003. He has received numerous awards, including Best Paper Awards, Outstanding Thesis Advisor Award, Outstanding Service Award from IEEE Technical Committee on Communications. He's a fellow of the IEEE and the ACM. So it's with great pleasure I introduce Professor Amma.
Thank you, Anurag. I have to tell you, I find these introductions, so thank you for the introduction, by the way. I find them quite intimidating. I think the better introduction would be, our speaker today couldn't make it. So we went out the street, we found this guy, said, can you give the talk? He said, I can give a talk. So that way I don't have to live up to this kind of introduction. But thank you very much for inviting me. It's my first time to Fort Collins, not the first time to this area. I have relatives in Colorado Springs, so we've been to this area a lot, but never to Colorado. And I love your weather. I wish they tell me that's true. It's always like this. So you're lucky. So I hope you've had a chance to look at this quote here. This is you can look up the actual full poem by William Cullen Bryant, and it's about, we should not complain about the world changing. In fact, we should really complain if things don't change. And this talk is really about that. It's about change in the area that I work in, predominantly the area of computer networks. I gave the title "The Time Traveling Networking Researcher and Other Short Stories," and you will see why I do that. I think the most interesting thing for me sometimes to look at is not to look at changes as they happen over time, but to try to look at what was and what is over long periods of time. And I think this device of looking at this time traveler is a good way to appreciate how far any field has gone, but in particular how far networking has gone over the years. So we'll start with that. So this is the time-traveling networking researcher. He has a DeLorean, as you all know. I hope many of you have seen Back to the Future. And we're going to call him Marty, okay? And one of the things I know how to do, in addition to everything else, is how to create these things with the actual date and time. So this Marty basically left in '85 and arrives today. And so, this is a networking researcher, so he doesn't care about anything else except looking at the state of networking before and after. So we'll look at it very quickly, but it's actually very enlightening and quite revealing to see what happened. So in 1985, And I take some liberty in the actual time and dates of these things. So I think this, so we look at 1985 and 2017 as the two data points. So in 1985, there was really no internet. Probably the best picture you can see of the internet is this. It's called the NSF-net backbone, which you can argue is the beginning of the internet as we know it. It had 6 nodes covering part of the U.S. But that's it. In 2017, and it's actually very hard to draw to even visualize what the network looks like. And the best visualizations come out of this group at called CADA. And this is actually a 2014 picture. And what it's showing you is the picture of the network today. The details are not really that important, but what is interesting to note is that where we had 6 routers here, this graph that they're showing has 70,000 plus nodes, but each node is by itself a several maybe tens, maybe hundreds of routers. Okay, so we went from 6 routers to maybe 700,000, 7 million routers, okay, worldwide. So the network really scaled up. Now, what we use the network for in 85 and in 2017 are quite different. In 85, probably the most high-tech application you could think of was file transfer. This was the technology of moving file, a program, a piece of text, whatever, from one place to another over the network. Today, of course, the internet is used for all sorts of things, video streaming, social networking, and so on. One thing that people ask me is, what about content distribution? So one could argue today that the network is really not about connecting people, but more about moving content, video, files, and so on from one place to another. And the interesting thing is this content distribution, I'll come back to this question, is a very important application that is not really a product of people thinking about what can we do with the internet. It was something that we've always wanted to do and we've always done. And one thing that surprises people is to look at systems that had content distribution even before the internet. And this is an example of these kinds of systems. These are systems that were called various names, teletext and videotext, and they were information basically being sent digitally over. The best thing we could do then was the television network, and sometimes on-the-air television. And they were doing things that we were doing today, travel, information, radios, and so on. If you can read, this may be too small for the back, but it says telesoftware. And telesoftware is basically a service that BBC, who was selling computers at the time, was actually allowing people to download software from their servers to your BBC computer. Okay, this is 85, no internet, no TCP/IP inside, nothing. There's nothing that you would recognize in the back end of this, and yet pretty much the applications are the same. The technology was different. Display technology, transmission technology, everything was different. But given what we could do at the time, we were in fact doing as much as we are doing today. Today, of course, it's a whole new world with video streaming and news and so on. The point again is that these kinds of services are not really enabled by the internet. We could conceive of them way before the internet, and we would have done them had the internet happened. Okay. Another interesting thing is how networking people did research. It's actually fascinating to think about this in detail, but let me give you some idea about this. In the 80s, and this is around the time I was doing my PhD, and I was kind of being trained in this area. Networking people really came from the engineering side of things. Computer science was not a very mature discipline. And engineers basically design and build things. So we were thinking, we had this goal of building networks. So we were going to design them. We're going to figure out what they look like, and then we're going to build them. And once they are built, we're going to sit back and enjoy. Basically maintain them, do things with them. Okay? And in that vein, if you look at the literature at the time, you will see basically this come through. So this is an example of a paper, again, that it's too small, but it says flow control and routing algorithms for data networks. It's by Bob Gallagher and Jamal Golestani from MIT. Bob Gallagher, if people know him, is a big information theory icon, had lots of contributions in networking as well in the early 80s, late 70s. If you look at this paper carefully and look at these two functions, flow control and routing, those functions continue to occupy us today. I mean, today there is research on routing and what people call congestion control, a derivative of flow control. At the time, if you look at this paper and you read it, you'll see that the idea was we're going to formulate it as a math program, we're going to solve it, and it's done. There was no illusion that this thing is going to keep going. We're just going to do it once we're done. Today, though, the people recognize this is not how it's happened and not what is going to happen into the future. In fact, it's almost like what I would call waking up to a nightmare in the sense that it's never ending. So what we realize over time is that what we're doing is build something. So you may design it, but you may actually a lot of times build it just because you want to build it. Then you do measure it, get experience with it, tweak it, and then go back and rebuild it, redesign it, rebuild it, redo it, everything. So everything keeps going forever and ever and ever and ever. Okay, it never stops. Okay, it might sound like, okay, this is how we should do it, but this is not the mindset of a lot of engineers in some sense. Okay, the research actually reflected this quite heavily. There's something else too, and if you're in CS, you recognize that basically we disseminate our research results through these conferences that become essentially archival. And SIGCOMM is the kind of main conference, one of the most prestigious conferences. But in '85, first of all, there was no such thing as a prestigious conference. This idea kind of came later. The conferences were about sharing results and brainstorming. But in '85, what's interesting, if you look at the number of authors per paper in SIGCOMM '85, you'll see the average was 1.9. Many, many papers with only a single author. The maximum number of authors of any paper was 3. Again, the window and flow control and so on was occupying people as a research question. Today, though, I just did these statistics. I updated the talk with these statistics. But basically, in 2017, SIGCOMM had 36 papers. The average number of authors per paper is 6.3. There is one paper in the whole program that had 2 authors. I've done this over the last maybe 5-6 years. 2-author paper is an outlier. It's probably the only 2-author paper that showed up in SIGCOMM for the last 5-6 years. Minimum before that was 3. But the maximum is 24. There were actually one paper with 24 authors, one paper with 21 authors. Okay. Now, if you think about it, there are lots of implications of this, but one of them is that basically academics cannot do this kind of work. These papers, the 24 and 21 authors, tend to come from industry. Google, I think, the 24-author paper, and so they are a big player in these conferences today. My research, of course, tracked this, and I do this for entertainment purposes to show you what I looked like in '85. But in fact, I was doing very similar kind of work. I had this single author paper from, this is Transactions on Communications. A lot of kind of math and thinking that, okay, this is going to solve it. Today, my work is much more system-oriented. This is, 5-author paper I did with some colleagues at AT&T and one of our students. But again, the work is very much in that flavor. So I think pretty much, I still haven't figured out how to do the 24-author paper. But maybe that will come. Okay, so this is the time traveler, okay? And you can see there's huge changes, okay? The rest of the talk now is about trying to understand how these changes actually take place over time, right? Not the big step from '85 to 2017, but trying to track the progress, trying to understand and model it. The first thing you should realize, I'm not about to rewrite networking history. What I want to do, there's a lot of good references for that. What I want to do is add some structure, and it's actually going to be very simple structure to the history that will help us understand and kind of predict and see new things happening. I'm not going to talk about my research. There may be one thing, but this is not about my research in general. You can consider this whole idea as a kind of a research, but it's not very technical. I give another talk at 2 or 3 o'clock. That's actually more about my research. So I want to not have to worry too much about what I say. So if it sounds critical or whatever, I'm just as guilty as everyone. I'm looking back. So hindsight is 20/20. I have that benefit. So I don't really mean to criticize anyone or anything in my talk. So okay, so the way I'm going to structure this is in these 3 other short stories. You can think of them as my trilogy. Academics don't get to write these volumes. Knuth wrote, you all know, the volume 1, volume 2, volume 3. I don't see academics do this very much anymore. But this is mine, okay? But it's PowerPoint. So what I'm going to do is tell you 3 stories that eventually, hopefully, will tie into something. Again, not Game of Thrones, don't expect that, but something. So we're going to first talk about this process that actually I think underlies all developments, but certainly network development, which is necessity is the mother of invention. And then we're going to, I'll leave these to be mysteries. We're going to do this oscillation from many to one and then back from one to many. Okay, with these. I had to learn Latin to put these titles together. So, okay. And then let me give you what I think you should get out of this, and hopefully you can question me if you don't think I've made the point clearly. So the first thing is I will tell you that the way we get to anything, I think in networking is through this iterative process. Okay? And that iterative process is fundamental. If you ever get in its way, things start to go haywire. The other thing I think, and I hope to convince you of this, that basically today we think of networking as satisfied with this one internet, this big single network. And I will argue that there's nothing fundamental about having one network do everything. Okay? There's certainly advantages, okay? But there's nothing fundamental about that. And then argue that this iterative process that we are that basically we've experienced and will continue to experience forever is actually changing the paradigm again from the single network world to this many network world. Okay? And that many network world is not a bad thing. In fact, this is a good thing that it will just open up the networking research agenda for many, many years to come. Okay? So let me start with the first story. So the first question is, you've all heard necessity is the mother of invention. The question is, what does it really mean? And in networking. So when you talk about networking, necessity could be that you want to support service. That's something you want to do over long distances. Digital service, content distribution. And you want to support scale. So we'll come back to this question of scale. Scale, and I'll say this many times, scale is what drives networks. In my networking classes, I tell them, it's actually easy in 1.5 hours, 2 hours to tell them how to network 2 machines. Take 2 machines, connect them, get them talking to each other, sending files, sending video, what have you. Okay, that can happen really quickly. And then I tell them the next 14 weeks about understanding how to do what I just did with 2 machines with just many, many more machines. So basically networking is all about scale. So supporting scale is also a necessity. What invention is for networking is basically the infrastructure that we're building, the deployed infrastructure. So you can translate necessity as the mother of invention to this service or scale support motivates infrastructure deployment. And to put this pictorially, that we'll come back to this picture, but basically you can think of, I have a network service or I have certain scale that I want to satisfy, and then you deploy infrastructure to satisfy. Now, one thing unique, not necessarily only about networking, but certainly important about networking is that the service or the scale keeps changing. And I'll show you some numbers, but basically we are not in a static position when we look at scale. Scale, and certainly our concept of what we can do also keeps changing. As the network, the services change and the scale changes, what we find is we have to repeat this process. Okay, so this is basically an iterative process that we have to go through. I'm going to call this the service infrastructure cycle, sometimes just the cycle to simplify life. And this is how we got to where we are. Okay, so let me talk a little bit about scalability because that's important. Again, I tell my students, this is in the graduate course, I tell them if I ask you a question, you don't know what the answer is. You say, why are we doing this, or why is this the way it is? Or what's the challenge, or whatever. And if you have no clue what to say, if you say scalability, 90% of the time you're going to be right. So scalability is it, right? So what scalability means, the ability to handle a large number of connected entities. This large is a relative term, and if you look historically, it starts with a small number and goes up over the years. It has been the main driving force, and will continue to be the main driving force for developments in networking. And today we have 3 billion internet users in a world that has 7 billion people. So there's a lot of room to grow. We have about 10 billion connected devices, about 3 1/3 per person. But that's predicted to go up. The numbers vary depending on whether you're trying to hype it or be realistic or whatever, but it's anywhere between 20 and 40 in the next 2-3 years, 20 and 40 billion. If you look at services, so it's not crazy to think of this kind of growth. I'll show you quickly. So these are kind of content video service scale. So and I've tracked it, for many years I've tracked it and I've kept these numbers. In '98, John Glenn went up on the shuttle and CNN broadcast this video live, and they reported there were 500,000 hits per minute on their webpage. In 2000, that's 2 years later, Madonna broadcast a live concert on MSN. They reported 9 million logged in, but if you look carefully at their experience, basically it can't be. My guess is maybe 500,000 of them were actually able to watch the concert live, because there were statements like this: "My nerves were broken down trying to get connected." So although they reported that number, I don't believe it. Fast forward to 2014, we get really more ambitious with real. Madonna is real, but this is even more real for most of the world. The Soccer World Cup was on ESPN, was broadcast live, and it had 1.8 million unique users. There was an NFL game that was broadcast live in 2015 by Yahoo, and they reported 15.2 million unique users. So you can see the growth in terms of scale of not only of people's interest, but also of our ability to deliver over time. So let's go back now to the service infrastructure cycle. Worked really well, and it produced the internet as we know it today, basically a single infrastructure that we use to deploy many services. Until around 2005, and people in networking will know this for sure, but there were people started to complain that the network was unable to adapt to new pressures and requirements. Okay, this is when we started hearing that although we think of this as being updating the infrastructure based on new services, around 2005 people said we are not able to do this anymore, and there are lots of reasons for this. I'm not going to get into them. The literature talks about those, but basically it was a true thing that was actually happening. And then they gave it a name, ossification. Okay, so ossification, of course, this is an old dog that is trying to be taught a new trick, and you can't do that sometimes. But anyway, it started getting this name, and it was showing up in these papers about the ossification of the internet, and that its inability to respond to new demands. Okay, that's serious if you think about it. That basically we have this infrastructure that we cannot make it do new things, but we cannot stop thinking of new things. So again, to explain it visually with this cycle, basically what happened is this: although we could continuously conceive of new things to do, we could not deploy the infrastructure to do it. Okay? This is not to say that since 2005 we're not able to do new things. People were getting very creative and were able to deploy new things, but by hacks, by patches, by all sorts of tricks. But fundamentally, we were unable to change the architecture of the network. So let me give you a quick run through to show you kind of an example of this in place. Okay. So I'm going to show two things that the network was asked to do, and how they developed over the years. And we'll do this very quickly. This you could take hours to explain, but I want to show you to kind of make the point that about the cycle and how it ossifies. So unicast routing is the function that the network performs to deliver data to a single destination. And this, as you might imagine, is a very important function for networks from very early on. You couldn't build a network without this function. Multicast routing, on the other hand, is the ability to send data to multiple destinations at one point. So what I'm doing now is multicast. I basically am speaking once and all of you are hearing me. I could replace this with taking each one of you on the side and telling them, giving them the talk separately. So it's not important. I mean, I could replace it. It's obviously inefficient to do this, but I could certainly fake it. Okay. So what happened is, as the network was starting to get deployed, unicast routing had to be in place. Multicast routing could wait. And this is what I just said, basically defining multicast routing. And as the internet grew in size, though, it got to be really complicated. And to show you what happened there is I use this picture. So this picture on the x-axis is the years from 1969 to 2015. On the y-axis is the number of hosts that these are estimates done by, and you can go to that website to see even more recent estimates. But this, we went from 5 hosts to 1 billion hosts, okay, connected to the network over this period of time. So if you look at unicast routing, you can place developments of unicast routing over this. There's a very early paper from 1962 by Prosser that kind of lays some fundamentals of routing. Then there is the details here are not important. The people who work in networking will know the specifics of the protocols. But it's important here to see that there was a progression of protocols. There's a protocol was called distance vector routing that worked really well for small networks. That stopped working as the network got larger, so it was replaced by another idea called link state routing. And then as the network grew even bigger, we could not actually build a single network. We had to do a hierarchy of networks. So we developed a protocol called exterior gateway protocol that kind of connected all the various pieces of the network. As the network grew even bigger, we had to have a different protocol called border gateway protocol. And that came in many variations until the last one was BGP4. So if you look at the timing here, you'll see that BGP4 was around 2005 was the specification, but also around 2005 was when the network ossified. And in fact, there hasn't really been a lot of deployment of new routing protocols within the internet since then, not for the lack of proposals. BGP has issues in terms of security, and people have proposed that, but yet those are having a hard time getting deployed. Okay. If you look carefully at the literature, you will see actually the cycle that I described actually being explicitly cited. So for example, when people were talking about BGP, they were saying things like BGP was built on experience gained with EGP, as defined and whatever, and usage. So experience and usage of EGP helped us develop BGP. Okay. So you can actually almost visually see the cycle in this statement, which is in one of the standard documents for BGP. Multicast had a different set of developments. With multicast, like I said, it's going from single user to multiple destinations, but all with one transmission. So me speaking once and everyone hearing me at the same time. Very scalable. It's very nice if I want to speak to a large audience. If the audience goes from a certain number here to thousands, I just need a bigger, louder, microphone and speaker, and I wouldn't have to exert any more effort. So basically, it's very scalable. And yet, and people recognize this, it also saves on the network. This is sending the same thing 3 times, and this is sending it with multicast support by doing data copying in the network. Okay, so it's actually also beneficial to the network. The problem with multicast is that as it developed, it did not really follow the cycle, and so we don't have deployed multicast today in the network. So to quickly show you what happened there is there's a lot of development in the early days of the internet, but probably the first development was a paper in SIGCOMM 84 by Lorenzo Aguilar that talked about how to deploy multicast in the internet protocol. In fact, the internet protocol that was deployed in 84 is identical to the internet protocol we have today, give or take a few bits, but basically identical. His proposal could have been probably deployed with maybe 10 lines of code in every router. There were probably 50 routers in the network then, so it was very easy to do. It had one problem, that he could only multicast to 10. So rather than multicast to a group like this, what I would have had to do is take 10 of you at a time, speak to you separately. It's still less work than taking one at a time, but it's not the scale that I would apply here. So it wasn't scalable to groups larger than 10. But if you look at the network then, the network had only 1,000 hosts. So saying I could scale to 10 was already big enough. I don't really need to scale to many more than that because I only had 1,000 in the entire network. However, what people thought at this time said, no, this is not good enough. We really need something to scale to a large group, and so we are not going to deploy this. And we're going to wait until we have something that scales to a large group. And with this, they anticipated. They were really thinking ahead. They're thinking about this 1 billion host network at a time when the network had 1,000. But the result of this is we have no experience deploying it. If you think about if we had to do this with unicast, if we said in the early days of unicast when the first unicast routing protocol was developed, if we said we're not going to develop it, it doesn't work for networks more than 100 nodes, then we would not have been able to develop further and further in routing. Here, unfortunately, because we could live without it, people said, okay, let's back off here and wait. And so they waited. They developed something even better. Actually, it had some problems, even though it could handle large groups. I'll fast forward through a lot of development. Eventually, though, there was something where people agreed is a good protocol. Something called Protocol Independent Multicast Single Source-Specific Multicast. Okay, the details are not important, but it's something that I think finally people agreed made sense from the kind of applications and the overhead on the network and so on. The problem is if you look at the timing, it's actually very interesting to see that this is around the time people were realizing the network is ossified. So to take the cycle is stuck, you couldn't actually put this in the network when you hadn't built up the experience and understanding from previous protocols. So basically, we do have multicast today, but it's in very niche kind of environments for stock quotes, for moving digital television, but not in the big internet that we all use. Okay, so this is the first story, okay, about how the cycle is important and we cannot ignore it, and how the cycle ultimately got ossified. So the interesting, so let's step back though. Before ossification, what people don't realize is the cycle took us to a place that it's one of those things that maybe does not have a unique convergence point. If you think about it, as you iterate over anything, you could find yourself here or there or there. So there is no one place you could have converged. But it led us to one point that we kind of accepted, but no, don't question. So, and this is the fact that we actually have a single network that is by and large carrying a lot of our services, if not all of them. This is like the Swiss Army knife that has many tools to do everything. And if you're a handyman, I'm not. But if you're a handyman, you do things. You know that you're not going to have a workshop with the Swiss Army knife. So it has some drawbacks. So, but let me step back now. So in 1987, this is kind of as the networks were getting created, we had this world of many networks. And in fact, you go to any textbook and you'll see many, many networks. They each had different purposes. They were each running different protocols. The one thing that happened though is that, and without getting into the full cycle, the full iterations of the cycle, what we found is eventually we have one network, and we take this for granted that it's kind of an underappreciated milestone in networking. It made sense because for a while, our main concern was just to get connected. The goal of the network was just to get a bit pipe from you to somewhere. We needed to do this scalably for very large number of connected people and devices. And we didn't have a lot of money, right? Economies of scale dictate basically you do everything in one place. So it made a lot of sense, right? So that's where we ended up. It had many effects. I'll go through them very quickly. Basically, networking research became a bit of an issue. And I remember those days, going from the many networks to one network. All of a sudden, papers and proposals were getting rejected not because the idea was bad, but because you could not deploy it on the internet. If you could not deploy it on the internet, why even work on it or think about it? Okay. So the other thing was, if you had an idea that you could deploy on the internet, people would say, prove it. Because this internet is where everyone is running things and I can't break it. So I have this great idea, prove that it works for me before I let you deploy it on the internet. So how are you going to prove it? This internet is large. I don't have this, this many machines or this many resources in my lab. So how am I going to do it? People started building these experimentation environments, and they had the M-Bone was for multicast, Q-Bone was quality of service, 6-Bone for IP version 6. Planet Lab and Genie were supposed to be more generic things. I'm going out on a limb here, and one could argue, I could argue with this statement myself, but I don't think any of them really succeeded in giving us this goal of, if you deploy it here, I will trust you to deploy it on the big internet. Okay, they had other benefits, but certainly not this ability to transition from experimental to deployment. If you think about it, though, if we had maintained the many network world, where we had many networks doing many things, we would not ossify. Just by definition, you cannot. The cycle would keep going, because if you cannot deploy it on one network, you build another network to do it. So by definition, having a many network world would not lead to ossification. But let me take a little bit of a digression here and talk to you about this one network agreement, because there's some interesting things. So because we had one network, we had to agree on one thing. And at the time, there were two different competing protocols, TCP/IP, which is what is used today, and something called OSI. Some of you may have studied at some point in networking classes. What's interesting, and this is the point I want to make, is that at the time, people really were saying strange things like, so this is from the same book by Misha Schwartz from '87. He's describing the two technologies, TCP/IP and OSI. He's saying TCP is an older standard. ISO is the standardization body that was making OSI. That ISO TP4, which is the equivalent of TCP in the OSI stack. And here's what he said. It's expected that TCP and TP4 will coexist for some time, but that use of TCP will begin to decrease. This is 87 is prediction. People would slowly stop using TCP. And it is of interest nonetheless to describe briefly some of the features of TCP here. So even though it's going away, I'll tell you about it anyway. The problem is, this is what I was teaching my students. This was everyone's teaching their students. It didn't come to be. This is not what happened, obviously. The point, this is a bit of a digression here, but I don't know what it is we are saying today that sounds like this. I don't know what it is that we're predicting will go away and will stay that actually sounds like this. This is very definitive. It's not hedged at all. So just be careful as you read the literature. Let me quickly tell you that there was the fact that we don't have OSI is not for the lack of trying. In '89, the U.S. government said, if you buy networking equipment, you cannot buy TCP/IP. You have to buy OSI. And this was called the GOSSIP. GOSSIP stands for Government OSI Profile. And there was other governments that said the same thing. I pulled out an article. Let me skip that. The IETF, which are the people that develop internet standards, were also saying the same thing. They were saying things like, we are fully committed to integrating OSI into the internet. We are taking sound technical steps to integrate OSI. Never happened. Okay. Again, if you're reading this at the moment from the people that are the competition to OSI, you're thinking, I should really study OSI, work on it, and so on. Anyway, there's an important point here. and actually, it's interesting is this. So slowly people started backing away. This is an article about Texas backing away from implementing OSI. At the same time, though, there is this article on the same. I pulled this for the OSI, but this is saying IBM has discovered something that we can show has better performance with TCP/IP, APPN, but IBM never really that particular set of protocols never really took off. Okay, so now this is the end of that second story. So the question is, we have one net and it's ossified, right? So the question is, are we done? I mean, it seems that if we have one network and we cannot move it, we cannot shake it to do anything, you should all go home. Okay, we should just study what this network, like we study, biology of an organism, just because we need to learn it. But there is nothing we can change about the biology of an organism. But actually, the story is not like that. So what is happening now is actually this one network is, in my opinion, and this is now where it gets to be a little bit speculative. Like Yogi Berra said, I'm predicting the future, and that's hard. So let's take this picture again. And I said this is something fundamental. And the moment we stop being able to ride this cycle, the moment we are done. But in fact, what's happening is the service demands and the scale are not stopping. We have increased scale. We have actually content providers now, Netflix, Google, YouTube, and so on. They are very demanding of the network, and they're not going to stop. And there is a lot of money and interest in those kinds of services. There's a lot of other application-specific requirements I'll mention. So basically what we see is that this service and scale thing is an unstoppable force. You can't really stop it. But on the other hand, the network is ossified and it's immovable. So you all heard the question, what happens when the unstoppable force meets the immovable object? And so what happens. What happens is, in this case, the immovable logic is going to break up. And this is now a bit speculative, but we're seeing some evidence, some early signs of this. So let me ask you a question that you may or may not realize. So we think of Google as the internet, but the question is Google now really the internet? And in order to see this, here's what I did. And for those who don't know, this is very geeky here, but this is a tool called Traceroute. And what it shows, the details are not important, but the point here is it shows that if you go, I'm willing to bet this happens here, but it certainly happens at Georgia Tech and at home. If I'm going from my home to Google service, I go through a few routers that belong to my ISP or the Georgia Tech network, and then beyond that, I'm straight into the Google infrastructure. So in fact, the internet is all about just my connectivity to Google. Not only that, once I get into Google, the protocol I'm using is no longer TCP. If Google is controlling everything, controlling the browser and controlling the service, I'm using something called Quick mostly, which is their own concoction. They're trying to standardize it, but it's their own set of protocols. Increasingly, well, this used to be the case, although Google is backed out of Google Fiber, but Google Fiber is in Atlanta, and so if you use Google Fiber and going to Google services, you are totally under the control of Google. There is no internet that we know, and the Google Fiber network will take you other places, but there is no internet as we know. The other thing that is happening is we are slowly moving from being just concerned about connecting somewhere to consuming content. And the content providers really have a lot of requirements. They want to control the interaction with the user, and they don't like to have anyone between them and their customers because they don't want anyone else to blame. Let me skip this picture because I'm running out of time. But basically, this is the current picture that we have now. You have an ISP. This is your connectivity. It connects you to the rest of the internet, but mostly it's connecting you to these content providers. Okay? Increasingly, these content providers are not only have this kind of connectivity, they're also embedding themselves into your ISP by putting servers or by having the ability to control some of the ISP functions. And so it's beginning to look something like this. This is what I call a zero-hop network. Basically, the users are essentially connected almost directly to their content provider. There is increasingly also, so this is clearly a fragmentation. This is now, you don't really see the internet as we think about it as single network. connecting you to different services. It's different networks connecting you to different services. There is now actually very explicit different networks. There is a network for IoT applications. Again, these are end-to-end networks that will carry a lot of traffic deployed everywhere. Sigfox is an example of that. There's a startup called Haste that is delivering very low latency for interactive games, again, by diverting you away from the internet and taking you through their infrastructure straight to the gaming servers. There is a network called FirstNet that's developed for first responders because they need prioritization, they need preemption and so on. They cannot ride on the regular internet. So there's a lot of these separate networks now increasingly being used for important applications. If you look at how people are thinking about the future of networks, there is something called 5G, fifth generation. It's really nominally about mobile broadband, but actually not everyone knows exactly what it means, and not everyone agrees what it means. But there is this concept of 5G slicing. And the idea of 5G slicing is the network is going to have 3 different slices for different types of services. For mobile broadband, high bandwidth essentially, low latency, and for large number of connected devices for Internet of Things kind of applications. And the pictures you see look something like this. They will actually explicitly show the network being divided into 3 different pieces. So this is kind of, this is not something that's happening. Everything else I showed you before actually are real deployments. These are hypothetical kind of architectures for the future, but you can actually see the slicing and the fragmentation already in place. No one is talking about delivering everything on the same infrastructure. So the question is, so what? Okay, so fragmenting, so what's the big deal? So the big deal, of course, is that this is a totally different paradigm from what people are thinking. So my argument is, we don't actually think about it that explicitly. There is a lot of implicit kind of discussion of this going on. But thinking about it explicitly helps us. It's a good thing because there is no ossification when we allow many networks, right? So the ossification is gone. And it opens up the research agenda. So no longer now are you worried about, is this thing deployable in this one network that I have? On the other hand, though, the one network had some advantages, right? The economy of scale is one of them. That is no longer an issue for some big content providers. Big content providers can justify, building unique infrastructure because there's so much money to be made for delivering their service to you. However, if you're a new Netflix that wants to start up, you can't afford this. So the one network had this advantage of having this what's called low barrier to entry. If you wanted to start a new service on the network, you didn't have to build a new infrastructure. It was there. It was neutral. It was working for you. So you didn't have to build it. And we will lose this in the one network. So in the many network world, so not one network fragments. So I think it's important to be aware of this and figure ways around it if we can. Okay. So this basically concludes the trilogy. We went from understanding that networking developments is an iterative process, and that iterative process has been challenged, essentially stuck for various reasons. We went back and saw that this iterative process produced the one network for us, okay, which made a lot of sense at the time, but the one network is ossified, which also stymied the progress of the cycle. And so the response is basically natural. People are not just going to give up on services. They will find a way around it. And it seems that there's a systematic kind of fragmentation of networks today to actually keep the cycle going. But there are concerns about that world, and so we have to be careful. But I think because of this, it actually, from a networking researcher point of view, it's actually a very exciting time because there is really no stopping scale and new services. Those people will keep coming up with them, and the scale will continue to increase no matter what. And so that there's going to be a continued drive for innovation in networking. Okay, the ossification will be a thing of the past. The many network world will be a way that we can get around it now, and people will stop talking about it at some point. There's one other additional feature that is a totally orthogonal piece that is happening, and I didn't bring it up here, but it's a very important piece, I think, to add to this mix, is that there's a whole area of network programmability that's coming up in the networking research, and including some deployments, that's actually going to add the flexibility. So if you think many networks and network programmability together is going to be just a powerful force to keep things going and keep things exciting. So let me remind you what the takeaways were. There isn't this fundamental iterative process, and we ignore it at our own peril. The fact that we have a single network doesn't mean it's something that we should take as a given, and we should. And in fact, it's already fragmenting, and other kind of paradigms are taking shape. And this many networks is really a good thing. But I think we should be aware of it and kind of embrace it and encourage it. So thank you.
We have time for a few questions.
Okay, go ahead.
Are all of the new mini networks proprietary?
Yes and no. So the ones I described, so two of them are proprietary. Sigfox is proprietary, and Haste is proprietary. They're startups, and everything is closed. But they allow other outsiders to connect to them. The FirstNet is not. FirstNet is a government effort, government-supported effort. I think it's managed by AT&T, and allows anyone to connect to it. And I think the standards are open. Sigfox is an example of what people call low-power WAN. And low-power WANs are an IoT kind of Internet of Things phenomena. And the LP-WAN effort is open, is standardized and open, not proprietary. So it's a mix of the two. And I'm not sure which will eventually kind of maybe. Quick is Google developed, but it's open in the sense that they have published the standards. They're trying to push them through the IATF process. And there are some open source Quick that you can download and use and test. Christos.
Thanks, Mustafa. Great presentation. Thank you back. Long time. You mentioned in your talk that most users today care about content. And there is a new area, if you like, that's looking at called information-centric networks, as opposed to corporate networks.
Right.
I was wondering what you think about that, right?
So to the extent that so we don't get any of our content today over information-centric networks, right? That's true, right? So in terms of deployment and kind of commercial success, if you will, it's not there. And I would say so there's information-centric networks. It had a lot of good backing at some point. The ideas are wonderful. I think they're also kind of so. It'd be nice if we had a many networks and someone would have built an information-centric network on the side and show and actually develop, deploy real services on it and so on. I think it got held up because of our inability to take it and kind of retrofit the network with what we needed. So it's kind of an example. It's one of the many different ideas that people have had over the years that basically got stuck, because we couldn't test it and deploy it, and because we couldn't test it and deploy it, we couldn't prove it would work. But I actually see maybe the many networks we'll see a resurgence of these ideas. Maybe someone will do a startup and say, okay, I can build something on the side with that.
I have one question.
Okay.
So is the net neutrality debate used at this point?
So that's an interesting question. I mean, so net neutrality is clearly, if we have a many networks, it will go away, right? Because then the concern, net neutrality comes from the sharing question. The other thing I think you should realize, in my opinion, net neutrality is basically an illusion, even when we enforce it in the network sense. Because when people talk about net neutrality, they're talking about very low-level networking things. This thing with the Google Quick, the reason Google deploys Quick is it's better than using TCP, HTTP, and TCP. So even if the packets are delivered in a neutral way, because you have the end-to-end protocol is different, you're going to get better performance. So I think the arguments about trying to enforce some neutrality in the guts of the network is kind of okay. I mean, it has some value, but it's not going to give us true end-to-end net neutrality. There's a lot of other things that are affecting the quality of experience and the quality of service, and the net neutrality is focused on one piece, and the others there's a lot of other stuff around it. So I think in many networks, certainly net neutrality will go away.
You mentioned that TCP/IP 1/4, right?
Yeah, yeah.
And you also mentioned that Google is using their own proprietary.
Mm-hmm.
Now, they don't want TCP/IP, they are going TCP.
Yeah.
I know that you said that there is no fundamental reasoning about this local network, but do you think that there is some reason why one set of protocols is being preferred, why people are looking for alternatives to TCP/IP?
It's just performance, and I mean that is the driving force, right? Google is preoccupied with shaving, milliseconds, sometimes sub-milliseconds, from your response time to their services, and they do all sorts of things. Quick is just one of their efforts to get things. I mean, just the name, right? Before that, they had something called Speedy, so they're not even trying to hide why. So they basically want things to happen fast, so that their services are running fast, and I mean this is a good thing, and so that's their main rationale for doing it. Well, I mean the TCP over IP over OSI is a longer discussion, and I had a slide there, but I didn't have time to go over it. But it's the standardization process of TCP IP was we make it work, then we standardize. The OSI people said let's write the document, then try to code it. And by the time people wanted things, the OSI, the standards were beautiful, but there was no code. TCP IP had the code running, so people went with it. That was
one more question.
So I love the idea of the many nets idea.
Okay.
Obviously that's wonderful for researchers and also for consumers. I am, however, concerned that can these many net ideas be applied to the end user? So typically, the way we are connected to the internet, we have one ISP.
Mm-hmm.
And we are at the mercy of that ISP.
Right.
And you sort of hinted that sort of a dystopian future of networking might be where we each connect to our ISP using some proprietary protocol between us and the ISP. And then that ISP connects with other ISPs, potentially using a different protocol, and then the end-to-end connectivity goes away.
So I didn't imply that. I didn't mean to imply that we. First of all, it's dystopian at all. I think I want to put a good face on this. I think it's a good thing that's happening. But certainly I think this first hop or last hop connection from a user to the ISP is going to have to continue to be one thing. Okay. Now what happens once you're inside the ISP? It's then between the ISP and the content provider. And in fact, it's already like that. Netflix will put Netflix servers inside the ISP. The ISP will provision resources inside their network to get you to the Netflix server, but only if you're a Netflix client. And so already once you get inside, the ISP is now doing all sorts of magic that maybe differentiates between different services. That will continue. But I don't think it will ever happen that we will have 5 plugs in the wall or have to reconfigure our laptop because now I'm using Netflix versus I'm using something else. So the access protocol and the access link will be the same, I think. It has to be. And that's true, in fact, in the Haste, all these examples, Haste, the FirstNet and the one thing actually that's unique is the Sigfox, the one with IoT, has a different wireless. They actually deploy different cell towers, use different frequencies and so on.
So what I was saying is that, so that's true. What I was saying is that if all these other networks become available, as users, as end users, we're still at the mercy of the ISP we connected. So are we also at the mercy of what our ISP agrees with the other networks?
A quick answer: we are at the mercy of that. But you have to rely on that agreement making sense from the customer point of view. Okay.
So 3 o'clock, room 300, student center. I want to present this token of appreciation presented to Mustafa Ahmad in appreciation for the Information Science and Technology Center seminar, distinguished lecture, Colorado State University.
Thank you. Thank you. Thank you very much.